there. You have a paper with Benjamin Weiss. Purposeful phase is a form of culturally appropriate intelligent disobedience during human-robot social interaction. Do you want to share your screen?
Yeah, sure. Hold on, let me put my slides up here. Yeah, first of all, thanks for the interesting discussion. I was listening in. I didn't want to interrupt. It was quite interesting, definitely relevant for a lot of our work, but a lot of interesting ideas, I think, from the group here. So definitely a lot of things to think about. So, all right, can you see my screen?
I can.
Okay. Well, then I'll start talking. Okay, sure. So my name is Dr. Casey Bennett. I am currently at Hanyang University in Seoul, South Korea, which is why I couldn't do the earlier one, because the earlier session was at like 2 in the morning here in Asia. So, but happy to be here and happy to talk to everybody. Hold on one second. There we go. Okay. Yeah, so obviously I'm American, even though I'm here in Korea. So, but I work with Dr. Benjamin Weiss, who's from Germany as well, on this project. And today we're going to be talking about a project we've been working on for a while here, looking at cross-cultural differences in the way people respond to robots. In particular, something that when we saw the workshop, we thought was really interesting about how sort of violating social norms affects people's perceptions of intelligence in the robots. So some of the things similar to what you guys were just talking about in the discussion there, but one of the open questions in intelligent agents and HRI and stuff like that is how we can try to trigger an intentional stance in humans relative to our artificial agents, right? Whether those are robots or virtual agents or whatever. If you guys are all familiar, I'm sure, with Daniel Dennett's work and that kind of stuff, is what causes people to perceive humans as intelligent, but our microwave is not, and then there's a whole range of things in between. Well, one of the questions is how do we kind of trigger that? One of our ideas in recent years has been looking at these situations where, kind of similar to what you guys are talking about with the rebellion, is when there are breakdowns in the interaction, sometimes those actually can cause people to perceive the agents as more intelligent, or at least more intentional, right? Versus something that just does what you tell it to do all the time, right? So these breakdowns, these failures are sort of like a form of defiance, I guess, in a sense, that we think can actually cause people to perceive the agents as more intelligent. But one of the things we've been noticing over the last couple of years, both in this study and some other ones we're running right now here in Korea and in Europe and in the United States, is that this seems to depend on the cultural and linguistic setting within which the experiment takes place. That different people, based on their cultural background or even the language that they're speaking, are going to perceive these kinds of breakdowns, these sort of violations of social norms, in a different way. So here today, I guess I only have 5 minutes, so let's very briefly summarize. We wanted to test that in a particular sort of human agent interaction. And to do that, we had to create a scenario where we could customize the agent and we could customize the environment, because we wanted to manipulate both of them to see the impact on the interaction, on people's perception of the agent. And we focus mostly on speech in the particular study. It's an obvious modality to focus on, but of course, as you guys are mentioning, if we here we have a virtual agent actually, but if we had an embodied agent, obviously we could look at other types of modalities, interaction modalities. So to do this, we actually took a video game called Don't Starve Together, which is a cooperative survival game. It's similar to Minecraft. It's very popular with the kids, as far as I understand it. And what we did is we hacked the game open so that we could modify it. And then that allowed us to sort of record game data and create customizable interaction scenarios. And then we could feed that game data back into the agent so that the agent could speak autonomously about things that were going on inside the video game. So while the player was playing the video game with this agent, the agent could actually talk about, we're fighting monsters, we're collecting resources, we're building things, all the stuff that you do in those kinds of, Minecraft-like survival games. The agent we built was capable of autonomous speech interactions. So there's no Wizard of Oz here. It speaks on its own. We've created like a speech hierarchy, and it can both hear what the person's speaking and create its own responses. And the agent's bilingual, so it can speak both in Korean and it can speak in English. Obviously, I'm in Korea, but I work with a lot of Americans. I'm American, so we're running the study in multiple places and looking at different responses of different people. For this particular study, this is part of a larger project. For what I'm going to talk about today, we ran 32 participants, 16 Korean, 16 English. We let them play the game with the agent for 30 minutes. We collected the Godspeed scale, which is a common HRI instrument for perceptions of robots and agents. And then we use the network mind scale to measure social presence. There's lots of things we can manipulate in an experiment like this in the speech interaction, but for this experiment, we were particularly interested in something called social IOR, or inhibition of return. So if you guys are familiar with computer vision or human visual systems, one of the things we know is that humans suppress information, or they suppress sort of the repetitive behaviors while they're doing information gathering, because repetitive behaviors are often not really all that functional. If we've already looked at something, it doesn't make sense to look at it again. It's better to look at other parts of the scene. And in the same way, when we're interacting with other beings, whether they're humans or other social entities, repetitive behavior often is actually not really very functional. If we've already said it, there's no reason to say it again. And moreover, repetitive behavior can be viewed as kind of weird, or also sometimes aggressive. If people say things again and again and again and again, right? You say something and you say it again, people are kind of like, right? It can be viewed as kind of aggressive, or a violation of social norms. So we tested this by basically turning this on and off. In the experiment, we basically implemented social IOR by having the agent not repeat something from the same categories, from the same kind of speech categories. So they've already said something about monsters, they don't say something again for like up to 3 seconds. Or if they say something about food, they don't repeat something in that same category for a short period of time, like 2 or 3 seconds. And we turn that on and off. And what we were expecting, our null hypothesis, is that there'd be no difference between the cultures and between the languages the agent was speaking. But that's not what we saw. In fact, what we saw was in the Koreans, really, there was no difference between the two scenarios. But English speakers actually thought the agent, when it was a little bit more aggressive, they thought it was had more social presence. They felt like it was more engaging and more interactive, although they didn't like it as much, but they felt like it was more lifelike, which we thought was really, really interesting. Koreans did not have that same perception. In both situations, they didn't really think it was very lifelike, or they thought it was engaging, but they didn't really like it either way, which we thought was interesting. So to sum up very briefly in my 5 minutes, the idea here was that the effects of social IOR seem to vary by language and culture in unexpected ways. And we view kind of social IOR as one way to kind of create these implicit, I think as David was mentioning, these implicit forms of defiance rather than explicit. And we're also looking at doing other things. We're currently running many experiments around this, looking at different levels of chattiness, having anticipatory speech, so talking about the future instead of just talking about what's going on right now. And then also looking at doing bilingualism experiments. We actually switch the language within participants with people who speak both Korean and English, and then we switch it back and forth and look to see if there are differences in that. So the main takeaways from this, one of the things that's really interesting is past research, some of our own research included, has shown that cultural homophily, so having an agent that's adapted to certain cultural norms and behaves in those ways doesn't necessarily correspond to higher ratings of the agent. So it doesn't necessarily mean people think the agent is better, they like it more, that it's more intelligent. Actually, sometimes we get the opposite effect, and it's not really clear why. And one of our ideas is because agents that always do what they're supposed to are kind of people actually, it was interesting, Rick mentioned this. I actually would argue the opposite. People don't trust them. They view them as a little bit unintelligent and kind of more like a toy than like an intelligent agent. So trust is kind of a weird thing, I think. I think it can go both ways. And sometimes always doing what you're told kind of makes people think you're kind of stupid. That's what we think, at least. Of course, this is something we're still working on. And we're actually running other studies with physical robots where we put pets into people's homes, these robotic pets. We're doing this in Korea and the United States right now, and we're actually seeing something very similar, where the response, the perception of people is different when we kind of have the robot interact in particular ways. So that's my presentation. Hope you guys enjoyed it. Thank you.
Thanks very much. Appreciate it, Casey. So any questions from the audience? So just if I can just make sure I understood an important point here, Casey, sorry, I hope I'm not being socially incompetent here. You write, so removing social IOR seems to make the agent more engaging but less likable in English speakers only. I just want to make sure I got the referent right here. So the English speakers thought it was less likable, but both types of speakers thought the agent was more engaging?
The Koreans thought it was more engaging, but they didn't. So the Koreans thought it was engaging. This is kind of a weird result for us. The Koreans thought it was more engaging in both situations, which I don't know why. I think here's our weird suspicion of why this is. So Korean is the way Korean is spoken is quite different from English. It's not stressed. And so kind of the current state of voice systems is kind of robotic sounding, these Alexa and stuff. It's very stilted. Well, that's the way Korean sounds normally. Actually, it's not a stress language. It's a timed syllable language. So what our suspicion is maybe it's a difference in the way the languages are constructed that's causing Koreans not to have that change, that difference. But we actually thought the Koreans would view the aggressive speech behavior like worse, but that didn't happen. So we don't know why. Honestly.
Thank you.
Yeah.
Any questions from anyone? Please speak up if you have one. Well, if there are no more questions, let me just ask one more then. And so you're moving into the interesting looking robotic pets. Will they allow you to not just replicate your results, so to speak, but do things that you wouldn't otherwise be able to test before?
Yeah, so this is something that we're actively working on. So obviously I work with Rabinovich at IU. Some of you guys may know Cindy Bethel at Mississippi State, and some of these people in the HRI field. We don't know. A lot of this is still like these robotic pets. They're still very much toy-like, but we do want to kind of take the sensor data off these and then kind of modify the behaviors. And we would, when I saw this workshop, I was like, that's actually really interesting, because this is one of the problems is how do we go from a toy to something that's actually an intelligent agent? And I think what you guys are talking about is a really interesting idea of purposely causing these kinds of, like, when your dog poops on the floor, you're like, God damn it. But also you realize that it's not a toy. It's like an intelligent being capable of its own intentional behavior. And we're trying to get to that point. And I think this sort of rebelliousness might actually be a part of that. And so it is something I think we want to explore. How we do that, we haven't figured that out yet. But I think it's a really, really interesting idea what you guys are talking about in this workshop.
You're making me think of an earlier point made by some speakers indicating that what might look like disobedience is really not. It's based upon the interpretation of the entire context. And here, the interpretation of the dog has to go. So,
yeah.
Okay. Well, thanks, Casey. I greatly appreciate your presentation, and good morning to you. So with that, we have one more presentation of a paper, and that's by Wanqi. If I have the pronunciation correct, please excuse me if I didn't. But Casey, would you like to, thank you, unshare and give the next speaker a chance to share his or her screen? Excuse me.
Oh, okay, I'm here.
Ah, good. Thank you.
So can you see my screen?
Yes, I can.
Okay. Then thank you for offering the chance to advise our recent work. I'm Wanqi. I'm from Nanyang Technological University in Singapore. This work is about how to achieve robustness in multi-agent communicative reinforcement learning. Here is the outline of the presentation. First, I will introduce the background. Then, I will introduce the problem formulation and the challenges about the problem. Following that, I will introduce our method to address the challenges, and then I will report some experimental results, and then finally, I give a conclusion about the work. First is multi-agent communicative reinforcement learning. This process is commonly formulated by decentralized partial observed Markov decision process with communication. As you can see this figure, when agents make decision, apart from making a decision or an action, they will also send a message based on its current observation and the message it received. And when it do the decision, it'll also lead to based on its own observation and its received message to choose action. And the second part is adversary training. In this the aim is to train robust models to defend against potential attackers, and our purpose is to find an optimal perturbation that lead the model make a wrong decision. And here we consider adversary communication, particularly within there are malicious agents, and for each of them, they hold a private adversary policy. That is, based on its historical trajectory, the message it received and the message it pretend to send, it will choose a perturbation. This is a message perturbation, and then it will combine the chosen perturbation with the message it pretend to be sent to generate a adversary message, and by sending such adversary message, it want to disrupt team cooperation. So the objective of this adversary policy is to minimize the joint accumulated reward of the team of his team. And we conduct the work based on two assumptions. First is Byzantine value, that is agents have in fact information on who are malicious. And second assumption is concealment, that is malicious agents don't communicate or cooperate with each other. We also want to find an defense strategy for the adversary communication. Here is the general framework. As we can see here, the agent I taken over by the attacker generates a malicious message. That is, tau I here is the historical observation of the malicious agent I, and based on this, it will generate a perturbation data here and add it to the original message, I'm out, I here, and it will generate an adversary message. And this adversary message will be sent to a communication protocol to generate the message received by another agent J here. And by sending this adversary message, as the state action value estimation of agent I will be changed, and it may lead the agent J make a wrong action. For example, here from A2 to A3. And our idea is in this part, that is before agent J received the adversary message, we design a defending system to avoid it being affected. Now we introduce how we modeling the attacking scheme. As we said before, each malicious agent holds a private adversary policy. So here is the policy, and then we assume that the perturbation follow a Gaussian distribution because it is the maximum entropy distribution under the constraint of mean invariance. And then we use a deep neural network to predict the mean of the Gaussian. And that is the output of this neural network, which parameterized by mu. The output is sent to a Gaussian distribution to construct the distribution of the perturbation, and then by perform a sampling, we can get a perturbation. We learn this neural network by the well-known PPO algorithm with a regularizer that force the generated adversary message to be similar as the original message. Then is the defending system. Particularly, we design a two-stage message filter for the defending. It consists of two modules. First is a alarm detector, which determine the messages that are likely to be malicious. It receives a message and decide which one is likely to be the bad one. And after this step, for those messages that are recognized as the malicious message, we use a risk constructor to recover the message. And we can see here the reconstructor here is a mapping from a message to another message. We want to convert the adversary message to its original message. And for the training of these two modules, the objective is to maximize the joint accumulative reward of the team. So for the first part, we also use the PPO to achieve this. And following that, we design two regularizer to facilitate the training. First one is that as in the training phase, as we load the ground truth label of the malicious message, so we use such signal to guide the optimization of the alarm detector. And the second term is that we use the ground truth of the original message to get the update of the risk constructor. After design such defending system, since the attacker can adapt to the defending system, so we further formulate the attack defender problem as a two-player zero-sum game to improve the worst-case performance of the defense system. Particularly, we want to optimize this max-min objective. That is, if facing the best attacker, how should the defender do? And we optimize this max-min objective by a game theoretical framework, policy space response oracle here. That is, at each iteration, it keeps a population of policies, and we empirically evaluate a utility table for the current iteration, and calculate a large equilibrium for current restricted game. And at each iteration, we expand the policy population by calculating the best response policy for the defender and the attacker.
Sorry to interrupt. Could you finish up in about 2 minutes?
Okay, sure. Next is the experimental setting. First, we consider three realistic types of communication. Here is that is communication with delay, local communication, and communication with limit bandwidth. Here is some result. We can say the learning curve for the purple line, the learning curve first drop, and after applying the defending system, the performance recover. And here is it's also considered our design method improve the robustness as the worst case performance is better than the baseline. There is a performance after we scaling to multiple attackers. Similar results are observed. Here is an observation. That is, after we disable each of the component in the defender, we can say the performance of the defender drops significantly. And this is how we to understand how our method work. So we can say, after applying the defender, the Q values of the agent can be recovered to some extent, and this is the message part. As you can say, this is orange message, and this is the message perturbation, and we add them. This is the adversary message, and this is a message after recovered. We can say that this message is more similar to this one, so which indicates our method works. Now here is a conclusion. So I think that's it.
Thanks very much. Could you put up your conclusion slide while we just have time for a couple?
Okay.
Thank you.
Sure,
Appreciate
sure.
that. So Ruth, I think you had one.
Yeah, I wanted to say, first of all, thank you for the presentation. One of the things I try to think about the connection of this work to rebel agents, basically, and we talked about the difference between adversarial agents and collaborative agents, and whether rebel agents can be adversarial. But here you also have a very unique case where you have adversarial agents, but you also have a team. So you talked about Byzantine failure, understanding who is the adversary and who are the agents that you need to disobey in a group. It's a different type of rebellion from what we discussed so far. Maybe can you elaborate more on a high level? How can you detect these specific agents and decide which agents you wish to rebel against. You like you have the framework where you can you can see when there is a misalignment, right?
Yeah. Actually, the detecting of the adversary message is based on comparing. It's because we have a global communication protocol here. It will gathering the message from all the agents, or the message from all agents. So at this step, it can do a comparison between the messages. And if a pattern of the adversary message is obviously different with the message received, the message sent by other beline agents, then it's likely to be adversary thing. Because I think the reason is that there is a central communication protocol which can compare the messages of all the agents.
But eventually, once you do recognize what agents are adversarial, you don't have any explicit way to disobey or rebel against them at this point. Maybe you have some thoughts on how to extend that.
Yeah, I think after, I think for the center communication protocol, after it detecting the adversary message, find it is alarming, and then it will perform a transformation for it to make it align with the message sent from other agents.
Mm-hmm.